This is your presenter Asloob Mudassar, and I am presenting slide number 115 of the course on laser physics. Question is, a laser system can have a finite gain line width where more than one wavelength can oscillate simultaneously, with the central wavelength having the highest strength known as laser wavelength. Describe methods applicable within a laser cavity by which the wavelengths other than the central one can be selected. So you see that in this question we have to address the techniques that could be implementable within a laser cavity so that we can select other possible wavelengths that are oscillating within a laser system. So we have to we have to find out the methods or the techniques by which we can select different wavelengths oscillating within a laser cavity. The answer is, a laser has a gain line width where one or more wavelengths simultaneously oscillate among the central wavelength, which is the strongest or the dominant one, referred to as the laser wavelength. You see that in an ordinary laser system, when the laser operates, it operates at a one wavelength, which we call a laser wavelength. It is a dominant wavelength, but besides that, other wavelengths are also emitted with a laser output. A laser may be acquired to oscillate. A laser may be required to oscillate dominantly at a wavelength away from the central one, for which a wavelength selective element is placed within the laser cavity. Use of diffraction grating as one of the cavity mirrors, use of a dispersive prism along with a cavity mirror, and use of a birefringent plate between two identical polarizers within the cavity are the three most common wavelength selective mechanisms. These schemes in one dimensions are shown in figure 115.1. That is, in figure number 1, we are going to show three schemes. That is, for example, this is our scheme number 1. This is our scheme number 2. This is our scheme number 3. And we are presenting these three schemes under the caption figure number 1. And the caption of the figure number 1 is three different schemes for wavelength selection mechanism. So we are going to explain these schemes one by one. So first of all, we are going to address this scheme. In the first scheme, a diffraction grating in the litero arrangement as one of the cavity mirrors is given an angular tilt to select one wavelength, say lambda naught, which is reflected back along the resonator axis. Thus, angular tilting provides a means of a wavelength tuning. You see that here we are using the grating in litero, which means that so this is an arrangement in which the reflected beam, incident beam, and the reflected beam lie on one side of the normal to the grating, as shown in the figure. So you see that the normal is shown by the dotted line and labeled with the capital N, whereas the incident beam is incident on the grating along the resonator axis. So when the beam is incident on the grating, the beam is also reflected back on the same path. This arrangement is known as litero arrangement. So the advantage of this arrangement is that when you tilt this grating, that is, you change the angle of this grating, that is, you rotate this normal N with respect to the incident beam, what happens is that you will be able to select different wavelengths. So if many wavelengths are oscillating along the resonator axis through the active medium, it means that many wavelengths are oscillating within the laser cavity. So if you want to select one of the wavelengths, you need to tilt the grating. So if you keep on tilting the grating, you will be able to keep on selecting different wavelengths. So that tilting mechanism of the grating in the little arrangement provides you a means of wavelength selection or wavelength tuning from a laser source. So different wavelengths can be selected from a laser source by tilting this grating. So this will provide an arrangement for the selective as a selective element. And the caption of the figure 1 is diffraction grating in literal arrangement as wavelength selective element. So this is our first scheme, and the grating in the literal arrangement is acting as our element for the selection of wavelengths, or which provides us the tuning mechanism for selecting different wavelengths from this laser cavity. And this grating is also acting as a mirror too. So this is also acting as a reflecting mirror. Now we are going to discuss this arrangement. You see that we have a mirror 1, we have the active medium, we have a prism placed inside the resonator, and we have also a mirror 2. And a wavelength lambda naught has been shown, which we have selected. And the caption of the figure scheme 2 is dispersive prism along with mirror 2 as a wavelength selective element. So this prism along with the mirror 2 provides a means of tuning, or provides a means of selecting a desired wavelength. The description is given in this paragraph. In the second scheme, a dispersive prism is aligned with its face close to Brewster's angle. The angular tilt of the prism chooses one wavelength, say lambda naught, incident on the mirror 2 normally, or for a given prism tilt, the mirror 2 is adjusted to reflect the wavelength lambda naught normally backward. The angular tilting of the prism and the adjustment of the mirror 2, or the rotation of the mirror about its axis, provides a means of a wavelength tuning. So what you do is that, suppose that many wavelengths are oscillating within a resonator, and you want to select one of the wavelengths to come out as an output beam from the mirror 2. What you need to do is that you need to tilt your prisms. So when you keep on tilting the prism, it means that you are keep on changing the dispersive orders of the prism to be incident on the mirror 2. And the mirror 2 needs adjustment so that the mirror 2 can reflect the incident mirror back on the same path. That is, the beam which is incident on the mirror should be at normal incidence. So by tilting the prism, this normal incidence angle can be violated and can be different from normal incidence. And we need an adjustment of the mirror 2 so that the beam is reflected back on the same path. So the prism and the mirror 2, these two elements together provides a means of tuning the wavelengths, or provide a mean of selecting desired wavelength from a laser cavity. Now we are going to discuss this third scheme. You see that there are two polarizers, polarizer 1 and polarizer 2. These two polarizers have the same axis. That is the axis of a polarization, or the Fourier transmission axis of the polarizations 1 and 2 are identical. And in between them, we have placed a birefringent plate. And the axis of the birefringent plate is shown. This birefringent, the axis of the birefringent plane is shown and is marked with capital A. The birefringent material is also placed at an angle close to as an angle close to, or at an angle equal to Brewster angle. And there is a mirror 2 over here. And the scheme is, the caption of the scheme is use of a birefringent filter between two identical polarizers as wavelength selective element. So let us read the description about this scheme. In the third scheme, a birefringent plate, for example quartz or KDP, with optical axis parallel to the plate surface. You see that we are using these two crystals. The condition is that these two crystals should be cut in such a way that their optical axes lie on their surfaces. So the optical axis is parallel to the plate surface and is placed at Brewster's angle to the incident beam, sandwiched between two identical polarizers with their axes parallel, which allow the electric field to be transmitted in the plane of incidence of the plate. So the electric field is to be transmitted in the plane of incidence of the plate. So for the plate, we have to satisfy two conditions. One condition is that the optic axis of these plates, that is quartz or the KDP, should be parallel to the plate surface. One condition is this. The second condition is this quartz plate should be placed at Brewster's angle to the incident beam from polarizer 1. And of course, quartz plate or the KDP plate, as we have shown in the setup, should be sandwiched between two identical polarizers with their axes parallel to each other. That is, the two polarizations have the parallel axes, which allow the electric field to be transmitted in the plane of incidence of the plate. For this scheme to work, it is required that the optic axis of the plate should neither be parallel nor perpendicular to the plane of incidence. So you see that this is a very critical condition. And if this condition is not met, the scheme will not work. So it is required that the optic axis of the plate should neither be parallel nor perpendicular to the plane of incidence. So you see that if the light is coming, we have to arrange the plane of incidence of this crystal in such a way that the optic axis of the plate should neither be parallel nor perpendicular to the plane of incidence. It is better that the angle made by the optic axis of these plates should be at an angle of 45 degree to the incident beam, to the plane of incidence, so that the light equally split up into two parts. So you see that when the light will pass through such a quartz or KDP crystal, what will happen? The light will split into two beams. One beam will be called the ordinary beam and the other will be called extraordinary beam. And this will happen within the crystal. The ordinary beam will face a refractive index equal to N naught, and the extraordinary beam will face a refractive index equal to Ne. That is, the crystal will behave as two different materials, N naught and Ne, to the ordinary beam and to the extraordinary beam. So when these beam, that is the ordinary beam and the extraordinary beam, will come out from the crystal, they will combine together, and we want that their combination should be such that they combine together to form a linearly polarized beam, which can easily pass through the second polarizer. So that's why we have arranged the two polarizers parallel to each other. Now you see that the thickness of the plate will matter, which is described in the next paragraph. If Lp is the plate thickness, the two beams will suffer a phase difference. Delta phi is equal to 2 pi over lambda times Ne minus N naught multiplied by Lp. So you see that I have taken the difference between the phases of the two beams. That is the Ne beam, extraordinary beam, and the ordinary beam. Here I am assuming that the refractive index of Ne is greater than the refractive index N naught. But for different crystals, N naught could be larger than Ne. But for our present case, we are assuming that Ne is greater than N naught, and Lp is the thickness of the quartz plate or the KDP plate, whatever we are using. Lambda is the wavelength of our incident beam, and delta phi is equal to 2 pi over lambda times Ne minus N naught times Lp. Now you see that this is the phase difference that will be produced by the two beams, that is the ordinary beam and the extraordinary beam, which will come out from this birefringent plate. So when they will come out, they would have suffered a phase difference or equal to delta phi. Now we want that this delta phi should be an integral multiple of 2 pi. So n is an integer, where n is an integer. When the two beams will combine in the same state of polarization, that is the linear polarized before entering into the second polarizer. So you see that this delta phi, which we are assuming that should be integral multiple of 2 pi, would ensure that the two beams, after coming out from the birefringent plate, that is, one is the ordinary beam, the other is the extraordinary beam, these two beams should combine in such a way that a linearly polarized beam is formed. And if our birefringent optical axis is arranged at an angle of 45 degree to the plane of incidence, then the magnitude of the two beams to which it is split, to which the incident beam is split, that is the ordinary beam and the extraordinary beam, then the amplitude of these two beams will be equal at an angle of 45 degree of the optic axis of the birefringent plate when it makes an angle with the plane of a polarization of the incident beam. So the linearly polarized light should be formed before it enters into the second polarizer and suffers no loss through the second polarizer. So you see that if the phase difference is different than integer multiple of 2 pi, what will happen? Then the axis of this linearly polarized light after emerging from this quartz plate will be rotated. And when it is rotated, it will make a different angle. It will make some angle with the polarizer too, with the axis of the polarizer too, and so some part of the beam is lost. So in order to assure that the beam is not lost at the second polarizer, we want that the beam which emerges out from the birefringent plate should have the same polarization as that of the polarizer 2. And for that one, we have described what should be the arrangement of the birefringent plate. So this will ensure us this condition, that is delta phi should be integral multiple of 2 pi. But when this condition is not met, our emerged beam from the birefringent plate will have a linear polarized light, but it has a angle rotated. It has a rotated angle with respect to the linearly polarized which entered into the birefringent material. So due to this rotation, when it will passes through the second polarizer, some part of the beam is lost because the electric field of the beam coming out from the birefringent material will not in line with the transmission axis of the second polarizer. So some of the beam will be lost. So in order to avoid the loss, we need to select the width of the birefringent plate LP in such a way that we can ensure that delta phi is equal to 2 times n pi, 2 times n pi, that is integer multiple of 2 pi. Beam loss is also avoided through the plate by setting it at Brewster's angle. So you see that Brewster angle ensures the state of a polarization to be fixed within when it passes through the birefringent material. So under this condition and in the presence of the ideal polarizers, the transmission through the system will be maximum. So if our polarizers are ideal, it means that no attenuation will occur at the location of the polarizers. And of course, our birefringent plate should also be ideal in the sense that the light loss should be very small. And you see that we have also ensured that the state of polarization should remain the same when it passes, should remain the same of the beam which is passes through the polarizer 1 should have the same state of polarization after passing through the birefringent material, and this should also pass easily through the polarizer 2 because the polarizer 1 and polarizer 2 have the same state of orientation. If the electric field makes an angle 45 degree with the optic axis, that is the A axis which we have labeled over here. For example, look at this one. We have marked it as A axis, which designate the axis of which designates its optical axis. So if electric field makes an angle 45° with the optic axis or the A axis of the plate, then the transmission is given by. So the transmission through that place will be equal to cos square of delta phi over 2, where delta phi is what we have mentioned is given by this relationship, that delta phi should be equal to 2 pi over lambda times Ne minus N naught, and this is multiplied by Lp, that is the width of the birefringent plate. And this delta phi for maximum transmission should be required to have value equal to 2 times N pi. So this is the transmission. So this transmission will be maximum under the condition that delta phi is equal to 2 times N pi. Because 2 will be cancelled, and then we have N pi as an argument of cos. And you know that with N pi we have a value of cos to be equal to -1, and we have a squared of this quantity. So we have 1 over here. So that theoretically the transmission will be 1 through this system. In 2 pi over lambda times N minus N naught multiplied by Lp, which is equal to, which we want to be equal to 2 times N pi for minimum loss, and for the orientation of the polarization to be the same at polarization 1 and at the polarizer 2. So this condition will ensure that the state of polarization remains the same, where n is an integer. So you see that in this equation I have two labels. I have marked two quantities, one in red, that is N naught is in red, Lp is in red, and this integer N is in red. And the other two quantities, which is Ne and lambda, they have shown in blue. So if you fix N naught, Lp and N, then the only possibility is left here to change is Ne. So Ne can be changed when you change the optical axis of this birefringent plate. So if you rotate this birefringent plate, you rotate the optical axis of the birefringent plate. It means that you change the value of the refractive index N. So you see that in this in equation number 1, if you by rotating the optical axis of the birefringent plate, you change the value of Ne. And you know that in order to satisfy this equation, lambda has to be changed. So some value of lambda, only those values of lambda which are oscillating within the laser cavity, one of such lambda will satisfy this condition for a particular value of rotation of the optical axis of the birefringent plate, that is for some specific value of Ne, for which the condition is satisfied and for which the lambda satisfies that condition, then such a lambda will oscillate through the laser cavity, and the emitted wavelength will be equal to lambda. So let me read the description. Where the integer is n, where the integer n, if fixed with the thickness of the plate Lp is also fixed, the rotation of the plate about the axis normal to the surface changes the value of Ne. So you see that by rotating the birefringent plate, you can change the value of the refractive index Ne. And this requires that the rotation of the plate about the axis normal to its surface would change the value of Ne. Thus, for a given plate, that is for a given N, Lp and N naught. So you see that if you have a plate, it means that you could choose N. You know that N will be set up automatically, but it has to be an integer value to be satisfied. Lp is the width of the plate, which is fixed, and N naught is also fixed by the plate. The rotation of the plate in the desired orientation changes Ne, and the equation number 1 is satisfied by different lambda, thus providing means of a wavelength selection mechanism. If Ne minus N naught does not change much over the wavelength selection range, then the difference between the two consecutive frequencies called the spectral range or delta nu FSR. Free spectral range is given by in equation number 2. So delta nu FSR is equal to C over Ne minus N naught times LP. So you see that suppose that one of the wavelength is satisfied. So one of the wavelength which were oscillating in the laser cavity, one of such wavelength satisfied this condition for a given value of Ne, because N naught Lp and N are fixed. So if you further change Ne such that the next wavelength is satisfying this condition, then the difference between that range in terms of wavelength or in terms of frequency is known as the delta nu FSR. That is the free spectral range of this instrument. Because you know that the other wavelengths cannot be selected. So if you select lambda 1 satisfying equation number 1, then of course when you set the value of Ne, when you change the value of Ne, then you see that all continuous range of a wavelength will not be satisfied, but only some other value of lambda 2 will be satisfying this condition. So the change in wavelength lambda 1 minus lambda 2, or the corresponding change in frequencies represented by delta nu FSR, or the free spectral range, will be satisfying this condition as shown in equation number 2. That is delta nu FSR is equal to C over Ne minus N naught times Lp. The last two schemes have been used in the visible and near infrared spectral regions, whereas the first scheme has been demonstrated in the mid-IR region. So you see that these were the three mechanisms that I described. That is scheme number 1, which is a grating in litro, and the tilting of the grating will provide you a mechanism for selection of the wavelength within to be oscillating within the laser cavity, and at the same time this grating in the litro also acting as a mirror. So this scheme can be used to select a wavelength and provides a wavelength tuning mechanism. The second scheme was this one. You tilt the prism, you select a different wavelength, but you need to adjust the mirror too such that the beam incident on one should be at normal incidence, so that the beam is reflected back through the prism to the resonator. So this will, that is the prism, and along with the mirror too, these two elements provides together a way of changing the wavelength, or a way of selecting the wavelength, or a way of tuning the wavelengths. The third case was one, that is the scheme number 3. So in the scheme number 3, you have a polarization 1, polarization 2, both have the same axis. The light is polarized and is incident on the birefringent material. Then you know that in the birefringent material, you have this axis of the optical axis of the birefringent material. You need to rotate the axis of the birefringent material so that the beam, after passing through the birefringent material, should have the same polarization state as that of the incident beam on the birefringent material, so that the beam without any attenuation can pass through the polarizer too, and of course be incident on the mirror too. So this is required, you know that, but in addition, you can also, you know that when I as just explained, through this birefringent material, the beam that will enter will be split into two beams, that is the ordinary beam and the extraordinary beam. So when these two beams will combine and will come out from this birefringent material, they will combine together, forming a linearly polarized beam. But we want this linearly polarized beam emerging out from the birefringent material to have the same polarization state. For that one, we need a particular width of this material. And we also want that this material should face this incident beam to be at an angle of Brewster angle. so that we can also have better so we can also have polarization states, same polarization states within the birefringent material. And when these two beams will come out, that is the ordinary beam and the extraordinary beam from the birefringent material, they will combine together to form a linearly polarized light. We want a specific width of this material so that we can produce, we can have an emergent an emergent beam from the birefringent plate to be linearly polarized with the same state of polarization as that coming out from the polarizer one or incident on the birefringent material plate, birefringent plate. So you see that these were the three schemes that I have described. The first scheme was used, has been demonstrated in the mid-infrared range, whereas the second scheme and the third scheme, they have been demonstrated in the visible range and in the infrared range. So this is the end of slide number 115.